In this video, we're going to do the setup for the rest of the problems that were on the worksheet that we were doing in class on whatever day that was, Monday, where we're trying to make a decision about what to do for each integral. So in this video, I'll do the step that transforms the integral into a new integral, but I'll just do one step, and then you can complete the problem. And remember, this handout, the online version, has the sheet with the final answers on it. So number 7, this looks a lot like integration by parts because it's not clear that there's a substitution that I could make where u would be part of this integral and du would be another part of it. So this is an algebraic function x times a trig function secant squared. So our LIATE hierarchy suggests that we would try u as the algebraic part and v prime is the trig part. And that really only can help if we were able to find v. So we have to be able to do the antiderivative of the trig part in order to be able to do this. But in this case, the antiderivative of secant squared is just tangent. And of course, the derivative of x is 1. So integration by parts will say this is x times tangent of x minus the integral of 1 times tangent of x. So that is one step in the integration process. To finish the problem, I would have to integrate tangent of x, and that's one that we have done before. But that would be the first step of the integration. In problem number 8, we see that in parentheses we have x squared, and we know the derivative of x squared is 2x dx, and there is an x dx in the integrand. So this is a case where there is something compound in the integrand whose derivative, or at least something close to it, x dx, is also in the integrand. So this suggests that we might want to try a substitution. So I'm going to use the letter z for my substitutions for all of these problems because I don't want to use u substitution and then get confused with my u's from integration by parts. So if z is x squared, then dz is 2x dx. And so the way I would see that, I would think, okay, well, that means that 1/2 dz is equal to x dx. And my rationale for doing that is that I know there is an x dx in the integrand. So I can just match equals for equals and get rid of that. I know that's not the way everybody does it, but I have to pick one way to do it. So that's what I will do. So this integral, the cosine of x squared part will just become cosine of z, and the x dx part is 1/2 dz. So I would put that 1/2 out front, and I have to finish the problem, I just have to integrate cosine of z dz. And of course, since it's a substitution problem, after I find that antiderivative, I will have to plug back in to get my final answer in terms of the original variable x. In number 9, I just have the arcsine function. And so there's no compound expression, so probably not substitution. And I see I even forgot my dx on here, so that's bad. And it's not one of the forms that we talked about. So that leaves us with integration by parts. And we have seen something like this before, where we like so much the way that inverse trig functions get simpler when we take their derivatives that we're willing to do integration by parts using u equals the entire thing and v prime equals 1. If we do that, then the derivative of arcsine is 1 over the square root of 1 minus x squared, and the antiderivative of 1 is x. And so one step of integration by parts is going to say this is x times arcsine of x minus the integral of x times 1 over the square root of 1 minus x squared dx. So again, this is one step in the integration process. To finish that problem, this now can be done using substitution. If you let z equals 1 minus x squared, then dz will have an x dx in it. So it's very similar to the substitution that we did here, because the x squared's derivative is going to have an x dx. So moving on to the other problem setup, in number 10, it's very similar to the two issues that just came up. I see that, again, I have an x squared here, and the derivative of x squared is got a x dx in it, and there's an x dx right here. So it's worth thinking about substitution for this one. Oops. So if z is 1 plus 4x squared, then dz is 8x dx, which means that in this integral, well, here I would rewrite that 1/8 dz is equal to x dx. So that would be my form of the substitution, because I can see that there's an x dx right there in my integrand. So knowing what x dx is equal to will allow me to do that part of the substitution. So I'll have 1 over z, the entire denominator is z, and then instead of x dx, I'll have 1/8 dz. So I would bring that 1/8 outside and have just 1 over z dz. And of course, finishing that is fairly easy, because that's the natural log of the absolute value of z. And then we'd have to substitute back in to put the answer back in terms of the original variable x. This one also would have been, might have been tempted to do this using a trig substitution, because we do have the form here of something squared plus something squared. So if you were thinking along those lines, I would encourage you to just go ahead and give it a try. It will work out just fine. There's nothing wrong with doing that. So an alternative here would have been letting x equal 1/2 tangent of t, and then what will happen, and that means dx will be 1/2 of secant squared of t dt. If you do that, then the denominator here just becomes 1 plus tangent squared of t. The 1/2 tangent t, when you square it, will be 1/4 tangent squared. So 1/4 tangent squared times 4 will just be tangent squared. So in the denominator, I'll have 1 plus tangent squared of t here. And of course, 1 plus tangent squared is secant squared. So this is a perfectly reasonable way to do it as well. But in this case, thinking about substitution right off the bat will be the easiest way. This definitely is easier than introducing the trig functions. But either way will work fine. Number 11, that would be really a little bit easier to make an assessment here if we recognize that this is really the same thing as x times e to the minus x dx. Having an e to the x in the denominator is the same as multiplying by e to the minus x. So that's really the same problem. And written like that, it's pretty clear that integration by parts is going to be the best option. There's not really a way to do substitution, and it's not one of the other forms that we've seen. And we know from our LIATE hierarchy that when we have an algebraic expression times an exponential expression, then the algebraic expression should be what our u is equal to in integration by parts. So if u is x, then u prime is 1. If v prime is e to the minus x, then v is minus e to the minus x. So the integration by parts here will tell us this is minus x e to the minus x minus the integral of negative e to the minus x times 1. And again, that's one step of the integration process. We would then continue by thinking about what this integral is, and that's not hard. And then you can check your answer against the final answer on the second page of the handout. And finally, for number 12, we have sine to the fourth, and this is the kind of a trig integration that we'd rather not have, because it's got an even power of sine and no cosines. So all of our normal ways of dealing with this kind of go out the window. And so what we learned is that we have to involve double angle formulas for trig. So the double angle formula here that will be relevant is going to be the one that writes cosine of 2x in terms of sine. So one of our double angle formulas for cosine is the cosine of 2x is equal to 1 minus 2 sine squared of x. the result of that, if I solve that for sine squared, then I get sine squared of x is 1/2 1 minus cosine 2x. So I'm just algebraically rewriting this equation, so we're isolating the sine squared on one side. But we have sine to the fourth of x, which is not just sine squared. So I have to work a little harder at it. So sine to the fourth is sine squared squared. And so that is 1/2 times 1 minus cosine 2x squared. How many parentheses do I have there? One more. Dx. So when I multiply this out, the 1/2 in front here, this will be squared. So I'll just pull that out. And if I multiply out the rest of it, it's 1 minus 2 cosine 2x plus cosine squared 2x. What I'm doing there is just taking this expression and multiplying it by itself with FOIL. So 1 minus cosine 2x times 1 minus cosine 2x. If I FOIL it out, it'll be these guys. And so that's all fine, except we still have an even power of cosine in it. The integral of 1 is easy. The integral of 2 cosine 2x is easy. The one piece that's still remains to be seen, let me just write this. So I have 1/4 times the integral of 1 minus 1/2 times the integral of cosine 2x. Easy enough. And plus 1/4 the integral of cosine squared 2x. And that last one is, that last one is the one that I have to wrestle with. So back to trig identities. What is the cosine squared of 2x? Well, there's a double angle formula that relates cosine squared and cosine of the double angle. In this case, you're doubling the angle 2x. So the formula would be cosine of 4x is 2 times cosine squared 2x minus 1. So this is the same identity that we talked about before. It's just that instead of the theta here, instead of theta here, I have 2x, and instead of 2 theta, I have 4x. This identity is true as long as this angle is twice this angle. It doesn't matter what the angle is called. So this would also be a true identity or a true instance of the double angle formula identity. So let me go some more room. This identity means that cosine squared of 2x is 1/2 cosine of 4x plus 1. Again, just solving the identity for the cosine squared 2x term. So what I eventually will have here is 1/4 times the integral of 1 minus 1/2 times the integral of cosine 2x plus 1/4 times the integral of 1/2 cosine cosine of 4x plus 1. So it requires that I use the double angle formula twice, once in terms of x, and twice x, and then the second time in terms of 2x and twice 2x. But eventually I'll have this down to integrals that each are not hard to do. This is obviously very easy. This is just 1/4 times sine of 2x, not too bad. Antiderivative of cosine 4x is 1/4 sine 4x, and there's another plus 1 there. So the trig identities break this down into integrals of cosine 2x and cosine 4x, but those are much easier than ones that have powers of sine or cosine. I did go over the first 6 in the same way in class, but if you have questions on any of the first 6 about finishing the details, please just send me an email, and I'm happy to explain more.